Hey everybody! Today we are going to talk about some geometric sequences, which are very similar to arithmetic sequences. If you remember when we did recursive and explicit formulas for those, right? Those were linear. They had a constant rate of change. So every time we're adding 4, we're adding 4, we're adding 4, we're adding 4. Geometric sequences are going to have a common ratio. So that means that they are exponential in nature. So let me give you an example of what that might look like. Let's say you had something like 2, 10, 50, 250, blah, 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 right? So you're going to be able to see it's a geometric sequence if we can multiply by the same number every time to get to the next number. So obviously, not always super easy to see this time. You probably can tell that that's 5, right? 2 times 5 is 10, 10 times 5 is 50, 50 times 5 is 250, right? Pretty easy to see, but not always, especially if it's like a fraction or something. So if you're not sure if it's a geometric sequence or if what the common ratio is, you can always divide backwards. So if you do 250 divided by 50, that's 5. If you do 50 divided by 10, that's 5. If you do 10 divided by 2, that's 5. And you can always do that because you already know all those numbers, right? So you can use your calculator, just divide backwards. That'll tell you what that common ratio is, right? So if I want to check, that's really easy to do it. See if you're always multiplying by the same thing. We are still going to want to be able to do those two types of formulas. We want to be able to write this as a recursive formula and an explicit formula. So let's talk about recursive first. The recursive formula for a geometric sequence is going to look like this. We still need a sub 1 equals whatever that number is, right? Our first term, we have to define the first term. And then the recursive part is going to be a sub n equals r times a sub n minus 1. So we need our rate, our common ratio, if you will, at what we're changing. And then these are always going to be the same, a sub n and a sub n minus 1, right? So basically what we're doing is we're taking our constant ratio, we're multiplying it by the previous number, that's going to give me my new number. And I can keep doing that forever and ever and ever. The explicit formula is going to be a sub n equals a sub 1 times r to the n minus 1 power. So here we're taking that first term and it's going in our y-intercept spot in our exponential function, if you want to think of it that way. And our rate, that's our constant ratio, is going in that spot. And then the exponent is just going to be n minus 1 because, like if we want the third term, we would do to the second power. Because to get the first term, you do to the 0 power. So it's kind of like one term behind. That's where we get the n minus 1 from. So let's take a look at what these are going to look like for our sequence here. Okay? So first off, for the recursive side, we know that a sub 1 means the first term. So I'm going to define that as 2. And then for the rest of the recursive part, we're going to have our rate, which in this case we said was times by 5. So we have 5 times, and this is just going to be a sub n minus 1. That's what the recursive is going to look like. We define the first term, and then we just do a sub n equals whatever we're multiplying each time times a sub n minus 1. So if I wanted to use this to find the next, right? If 2, for example, is a sub 1, and I want to find a sub 2, I can do a sub 2, plug 2 in for n minus 1, because that's the one before it. 2 times 5 is 10. And then if I wanted to do the next one, I could plug 10 in here. 10 times 5 is 50. And I could keep doing that, and it would always give me whatever the next term is. So that's really good to find the next one. The explicit side over here, let's do the same thing. So we have a sub n. The first term is still 2. Our rate, or our constant ratio, is 5. And that is to the n minus 1. So again, if I wanted to find like the 10th term, this is good, right? I don't have to keep going like I would in the recursive and keep finding the next one. I can plug in any number I want here. And notice what happens, just to kind of show you guys. This looks very much like our base exponential function, right? Like standard form of exponentials, if you want to think of it that way. Here's our y-intercept, which makes sense. That's my starting point. And here is my rate, and it's to the x power, right? So look at what happens here. If you want the first number, 1 minus 1 is 0, 5 to the 0 is 1, 1 times 2 is 2, right? That's why the n minus 1 is there, because we have to make it anything to the 0 power in order to get 1. So that's kind of tricky. But like, let's say now we wanted the, let's say a sub 10. We can just plug 10 in up here. So 10 minus 1 would be 9. 5 to the 9th is very large, times 2. And I can get that the 10th term in my sequence here is this number. Looks like 3,906,250. So that escalated quickly, if you want to put it that way. Cool. So there's my recursive and my explicit. It's very much, if you were good at the arithmetic sequences, it's going to really piggyback off of that. Very similar. Let's do one more of these, and we'll talk about both formulas. So let's say we had 16 4 1 1/4 1/16. All right, so maybe this time that's a little bit harder for you to see what's going on here. I can tell you that it's exponential decay, because we are decreasing as we go. And if you're not sure, you can just do 1/16 divided by 1/4. And it's going to give you that our common ratio here is 1/4. Each time we're going 1/4. 1/4 of 16 is 4. 1/4 of 4 is 1. 1/4 of 1 is 4, right? So there's our common ratio. So if we want to go recursive, our first number is 16. And then we go a sub n. We need our rate. So that'd be 1/4 times a sub n minus 1. So our first term, and then we take our rate times the number that we want to find, the previous number. So if I wanted to find what's a sub 2, 16 times 1/4 is 4. That's our second term. There's a recursive one. And then let's do explicit. And we know we start a sub n. Our first term, a sub 1, is still 16. Times our rate, which in this case is 1/4. And instead of to the x power, it's to the n minus 1. And there's our explicit formula. And now if I want to find something like, hey, what is the 12th term? Sure, let's plug in 12. So 12 minus 1 is 11. 1/4 to the 11th is very tiny, times 16. Ooh, gave me something really small. A sub, what did I say, 12? Let's see if I can change it to a fraction. Oh, I can't. I'll just write what the decimal is. 0.12345538. Yeah, that's good. Some more numbers. Probably I would write it in scientific notation, actually. Throw it back to scientific notation. Shout out. All right, cool. So that's our explicit and our recursive formulas for geometric sequences. I don't think it's too bad. It's very similar to the arithmetic sequences. So you guys let me know if that's something that you're good with, not so good with, and we can roll with that. Okay? All right. Catch you on the flip side.